Today's lesson we're starting our next unit, Unit 2 on chemical reactions. Chemical reactions are so important to chemistry, and one thing we definitely need to review and go over is how to write chemical equations, what they're all about, and make sure we know how to balance them. So this is a skill that you would have learned a little bit about already in some of your science classes, but we want to make sure you've got a good solid background before going on, because balancing is something that we'll use in the rest of our course and if you take more chemistry beyond that. So first thing we need to do is review why we balance equations. Hopefully you remember the law of conservation of mass. So this is an important law because it tells us what we should expect to see during chemical reactions. So it says during a chemical reaction, the total mass of your reactants is equal to the total mass of your products. Now, if you remember in a chemical reaction, reactants are what you start off with. There can be one or more, and they go on the left side of the equation. And then the arrow here says they are reacting or forming or producing new compounds. And that new compound or compounds are your products. They go on the right-hand side. So what this law is saying, the mass of all of your reactants, whatever you start off with, has to equal to the mass of all of your products. It might not be in the same distribution in terms of number of compounds, but the total mass when you add up whatever's there has to be equal on both sides. This isn't a perfect ideal scenario. Often in real life, there are errors that we can't control and we don't always get a perfect result, but this is what we should expect to see if there are no errors. So let's next review the different types of equations that you can have. So the first type of equation, word equations, you're only going to see the names of your reactants and products. Okay? There's no element symbols, there's no chemical formulas, nothing like that. So as an example, if we take a look, this would be a word equation here. We've got hydrogen gas as one reactant, oxygen gas as another reactant. If you have more than one reactant, remember you use a plus sign to add them together. The arrow here separates our reactants and products. So this reaction produces water. Word equations are good for descriptors, but in chemistry we like to use our chemistry language, our formulas and our symbols. So the first thing you would want to do to getting to a proper equation is write something down called a skeleton equation. And this is where we're going to change these names into chemical formulas. So this is where your nomenclature comes back already. You need to know all of those naming rules to do equations. So if we change those names into formulas, this is what we would get. H2 and O2, they're both diatomic molecules, and they form water. Now, at this point, a skeleton equation is not necessarily balanced. Sometimes it ends up being balanced because you don't need coefficients in there, but most often you're going to have to add those in after. So, what do we do next? After you have a skeleton equation, to get to a proper chemical equation, you're going to need to balance it. So when we say balance, it means we have to follow the law of conservation of mass. We just went over that. We know the mass of the hydrogen and oxygen in this example has to equal to the mass of water. So if there was 5 grams and 5 grams, then we would get 10 grams over here and so on. How do we make sure they're balanced with our symbols? We add coefficients in front of the formulas. Coefficient just means number. And we use whole numbers for the most part. And they act kind of like multipliers. And you can see in your chemical formulas there are numbers, there are subscripts that tell us how many of each element we have. So the other way of looking at it is making sure we have the same number of atoms on the left of each element as we do on the right. So you can see in this equation up here, there's 2 hydrogens here and 2 hydrogens here, so they're equal right now. But the problem lies with the oxygens. There's 2 on the left, but there's only 1 on the right. So then we would have to balance. So to balance this equation, we would put a 2 in front of the hydrogen, and we would have to put a 2 in front of the water molecule. When we do both of those, 2 times 2 for hydrogen gives us 4. 2 times 2 gives us 4. This is still 2 oxygens here. And the 2 that's here also affects that oxygen, so we know there's 2 of them. We will go over some tricks and suggestions for balancing in a few minutes. So those are your 3 types of equations: word, skeleton, and balanced. Next, let's do a quick review of how to write states and what states you can see in equations. Whenever possible, you want to include the state of the reactants when you balance your chemical reaction. There are 4 that you'll run into: solid, liquid, gas, and aqueous. To write the symbol for solid, it's just an S in brackets, L for liquid, and G for gas. All these are all lowercase. Aqueous, if you remember, means it's dissolved in water. So if you have something dissolved in water, we use aqueous or AQ. Again, that's also lowercase. How do you figure out states? There's a couple things you can do. First, what if you just have a pure element in your chemical reaction? You can just look at your periodic table, and most of them are color-coded something similar to this, like the one that's in our classroom. Solids are black, so these are all of your metals and several nonmetals. We've got liquids in blue. You know there's only 2 on the periodic table, bromine and mercury. And then gases are in red. We know there's noble gases, there are some halogens and some other diatomic gases. But if you don't remember the state offhand, your periodic table is a great source to find that information. Next thing to look out for, ionic compounds. They often need to be dissolved in water to do their reaction. There's a lot of rules with these ones. So you'll see more rules and ways to figure this out later. This is when we talk about something called solubility. And we'll see this when we get to double displacement reactions. Last way that you can always do, especially if it's a molecular compound that's not very common or you're not familiar with, you can look up the states from a table or internet sources, MSDS sheets. They often just abbreviate it to SDS sheets, anything like that. So for now, just to take the pressure off, unless there's information given to you about states in a question, we're not going to worry about them so much right now. But at the end of the unit, you'll have a lot of knowledge to be able to write the states in. So going forward, after we finish this unit, you'll be able to include the states in all of your work. So now we're going to move on to balancing and do a good review of it. To help you get started or do some review, here's some guidelines. And it's not rules, they're guidelines. They're there to help you depending on the situation. Some of these steps will be helpful in certain circumstances and some not. So these are just some things to consider or think about when it comes to balancing. So let's take a look at a few. No matter what you're doing, you always want to have a proper skeleton equation. And the biggest thing is having the formulas written correctly. If your formula is incorrect, you're going to have a great difficulty trying to balance the equation properly. Or if you somehow manage to balance it, it's still not going to be right because your formulas are incorrect. So it's critical that you keep up with your nomenclature and keep practicing. Next thing you're going to do, balance your atoms. So you want to start balancing, but try and look at the ones that have a larger number on either side of the equation first. Okay, so count all your atoms up, check what you have on both sides, and you could start with the ones that are largest, especially if there's a big difference. If something has 6 and there's 1 or 2 of the other, the number 6 should be your driving factor where to start. Often, you'll find hydrogen and oxygen show up in many places, so sometimes we'll leave those till the end, but sometimes not. That's kind of a sometimes rule. Next one. When we get to polyatomic ions, try and stick with them as a unit. They don't generally change from left to right that often. So if they're not changing from the reactant side to the product side, just count them as a polyatomic ion rather than trying to break down each of the elements separately. It'll make your life a lot easier. If you're not sure what this means, when we go over some examples, we'll come back to this one together. Number 4. Next guideline. If you have elements that are uncombined, things like if it was just a pure single element or a diatomic, these ones are the easiest to try and balance on their own because all you need to do is put whatever number you need in front. So these ones are sometimes best to leave to the end if they're quite busy. If you hadn't tackled your hydrogen and oxygen in complicated situations, this might be a time that you take a look at them. Often at this point, the hydrogen and oxygens often get balanced by taking care of the other elements. The last guideline, no matter what you do, is one that you should always check. Check your answer. Once you're done balancing, go back and look at your answer a couple minutes later, count your number of atoms, simplify your coefficients to the lowest terms. So if you have a bunch of 2, 4, 2, make sure they get reduced to 1, 2, 1. Okay? But always check at the end. This is the step that a lot of people just end up missing. So now what we'll do is go on and try and practice some balancing together, and there's several examples. So we mentioned just before this, we're going to try and ignore the states for now. So if you know some states, you can put them in, but not required or mandatory at this point. So here's an equation. It's a word equation. So what I want you to do, since you know your nomenclature rules, see if you can write out first a skeleton equation, and if you think you know how to balance this one, go ahead. And then when you're ready to check, unpause your video now, and then we'll walk through the answers together. All right, hopefully you've given this a shot. Let's take a look. So, calcium plus hydrogen monochloride is calcium chloride and hydrogen gas. Calcium is a metal, so when I balance it, I just need Ca. Next, hydrogen monochloride, HCl. Then calcium chloride, CaCl2, and hydrogen gas. Hydrogen's one of those diatomics, make sure you put a 2 there. Next, you want to balance. So that means you may need coefficients in front of any of these particular compounds. So when we start, this is always helpful, not mandatory, but a good idea, especially when we're just practicing. List the elements that you have down here. We're going to take a tally. There's calcium, hydrogen, and chlorine. I'm going to do the same on this side, but keep the order the same. So if you're comparing back and forth, it's a lot easier to keep track. You're not going diagonally and mixing things up. To start, I have 1 calcium, 1 hydrogen, and 1 chlorine. On this side, I have 1 calcium. The 2 here means I have 2 chlorines, and I have 2 hydrogens. So when I look, calciums look like they're balanced, but not hydrogen and chlorine. So what I want to do next is make sure that I balance the 1 atoms down here. Now, it doesn't really matter where you start. I'll pick chlorine here. So if I want to make 2 on the other side, I know I need to multiply this 1 by 2. So to do that, I need to put a 2 here. That's where my chlorine is. I can't put any numbers in between or on the end. The only place I can put them are in front. The 2 will multiply, and it will give me 2 chlorines, but the 2 also affects the hydrogen. So both of these are getting multiplied by 2. So now I have 2 hydrogens and 2 chlorines on the other side. And look at that, when I stop and take a look, calcium's balanced, hydrogen's balanced, and chlorine is balanced. So now I know my equation is balanced and I don't need to do anything else. When there's no number in front for a balanced equation, it just implies that there's a number 1. So typically we don't put any numbers here when there's number 1. But if it's helpful for you just to remember that, yeah, I need to put a 1 there so I don't do anything else, you can definitely try that. Let's try another example. So here's the next one. Calcium sulfate plus aluminum bromide gives you aluminum sulfate and calcium bromide. So same thing at this point. Why don't you try writing out a skeleton equation? When you're done that, unpause the video, and then we'll walk through how to balance this one, and we'll show you that polyatomic ion trick that I mentioned before. All right, hopefully you've got your skeleton equation. So here we go. Calcium sulfate, aluminum bromide, aluminum sulfate, and calcium bromide. And I've left some spaces here in case we need to put some coefficients in. Now, I want to count how many I have on the left and right. So I've got calcium. Here, because I have a polyatomic ion sulfate, I'm just going to keep it all together. Sulfate is always SO4. I can see SO4 is on this side. So I'm just going to keep them together. Next, I've got aluminum, and I've got bromine. Then I can write down how many I have. 1 calcium. No brackets around the sulfate mean I have 1. I have 1 aluminum and 3 bromines. I'm going to do the same thing on this side. And I'm going to keep my order the same. Here, the 2 means I have 2 aluminums. I have 3 sulfates. The 3 means I have 3 of everything inside the bracket. 1 calcium, and 2 bromines. Now taking a look, this is definitely not balanced. So at this point, you can start in a couple of places, but there's a couple of things you might notice. 1, the biggest number here is 3. There's 3 sulfates and 1 over here. And when you look down here with the bromines, there's really different numbers on both sides. 3 on this side and 2 on this side. So the only way that I'm going to get an even number of bromines is probably if there's a multiple that's common between them. So that might be a place where I might want to start since I have bigger numbers of bromines on both sides. So if I look for the lowest common multiple between 3 and 2, that means 6. So if I wanted to get 6 bromines, 3 times 2 is going to give me 6. That means wherever my bromine is over here, I'm going to need to put a 2. Bromine is here, so I'm going to put 2. 2 multiplies by 3 to give me 6. But I have to also look at my aluminum. Aluminum is also multiplied by 2. So now there's 2 of them. On this side, I also want to make 6 bromines. So instead of multiplying by 2, here I need to multiply by 3 because there were fewer to start off with. Where's my bromine? My bromine's over here. So if I'm going to put a 3 in front, 3 times 2 gives me 6. But the 3 also will multiply the calcium. So now I have 3. Now I need to take a step back. My aluminums and my bromines are balanced on both sides. The problem here now are my calcium and sulfate. I have 1 of each on the left, and I have 3 of each on the right. If you look, calcium and sulfate are all together. So if I want 3 of each, all I need to do is put a 3 in front. That means calcium is multiplied by 3, and the sulfate is multiplied by 3. So now once I've done that, I've got 3 and 3 for calcium and sulfate, 2 aluminums, and 6 bromines. And now I can see my equation is balanced. So this is one place again where that trick, if you keep the SO4 together, it's one less thing to worry about. Since it's the same on both sides, you can see that in the name and in the formula, just keep them together and it saves you from doing some extra counting. Let's try another one together. Next example is a combustion reaction. We'll talk more about combustion reactions in our next lesson. So again, here I want you to try and write out the formulas for some practice to get the skeleton equation. So pause the video and see if you can get the skeleton equation. And then we'll unpause and we'll do the balancing together. So carbon, dicarbon hexahydride, oxygen gas, carbon dioxide, and water. So here let's count what we've got. Carbon, hydrogen, and oxygen. 2, 6, and 2. Now on this side I have the same. But there's one twist. So let's look. Carbon, there's 1 of them. I have 2 hydrogens over here. In total, I have 2 plus 1, which makes 3. 3 oxygens. But because they're not in the same compound, what I'm going to do is do this little trick. I'm going to write 2 plus 1. So I'm still counting 3 here, but if I change something in front of my carbon dioxide, it's only going to affect this total. Or if I put something in front of my water, then I know it's only going to affect this total. So now I want to start taking a look. What can I do here? Here I've got 6 hydrogens. Here I've got 2. So you might think right away, okay, if I want to make 6, I might put a 3 here. So 3 times 2 gives me 6. So now I have 6 hydrogens. This will also affect the number of oxygens. 3 times 1 is 3, and I have 2 over here. So when I go and do that, 2 is going to stay the same, but now with the 3, this is 3, so that means 5. So I've taken care of my hydrogens. Since oxygen is by itself, we'll come back to that one after. Let's try the carbons. If I want to make an equal number of carbons, there's 2 here and 1 here. So if I put a 2 here, 2 times 1 will give me 2. But here, I have 2 times 2, which means now 4. So instead of 2 here, I have 4. I've balanced my carbons, I've balanced my hydrogens. Here's a problem. So you've got 2 oxygens here, but the problem is over here, right now we have 7. 4 plus 3 is 7. These are not nice numbers to work with. And if we try and balance them out, to try and get 7 and 7 on both sides, it's not going to work. What would I have to multiply 2 by to give me 7? Theoretically in our head, let's do this just off to the side. 2 times 3.5 would give me 7. That would work. But we don't like using fractions. But we're going to use them temporarily to help us solve this. If I wanted to write 3.5 as a fraction, I could also write it as 7 over 2. So what if I did that? If I put 7 over 2 here, the way that it would work is 7 times 2 is 14, divided by 2 would be 7. That would give me 7 on both sides. Now, in some places, you'll see fractions being used with balanced equations. But technically, fractions aren't a good choice because you can't really have halves of molecules. Oxygen is always O2. You can't have half of an oxygen molecule. So, this is a good trick to get you the correct numbers because right now it is technically balanced. But if we want to make it more correct, what we're going to do is get rid of that fraction. How do you get rid of fractions? We know we multiply the top and the bottom by the same value, depending on what you have. So if I put a 2 here, 2 over 2 would cancel, and I would be left with 7. But if I multiply this by 2, I have to multiply everything by 2. So if I did that, I put a 2 in front of here. If I multiply this by 2, my fraction is gone. If I multiply this by 2, I would get 4. And if I multiply 3 by 2, I get 6. So if I go back now and check what I have, carbon we multiplied by 2, so it's 4. 6 times 2 is 12. 7 times 2 is 14. Over here, 2 times 2 is 4. 4 times 2, or sorry, we had 4. So multiply this by 2, we would get 8. Over here, 6. 6 times 2 gives us 12. And this one times 2 gives me 6. And 6 plus 8 gives me 14. So for balancing this one, this is a trick you can use if you didn't figure it out by trial and error. No matter which way you solve, if this is too complicated for you, you should have a 2, a 7, a 4, and a 6 to balance this one. Not all combustion reactions are this tricky, but this is a good strategy if you get stuck. Let's try one more to finish things off. So, I want you to try writing out the formulas for these ones first. So pause the video, see if you can get your skeleton equation, and if you want to try balancing it, go ahead, but I'll show you another trick you can try with this one. All right, let's take a look at your equations. Phosphoric acid is H3PO4. Sodium hydroxide, NaOH. sodium phosphate, and water is H2O. Now, when I start looking at doing my counts, I've got hydrogen, I've got phosphate, I've got sodium, and then I've got the hydroxide ion. So if I start counting, 3 hydrogens, 1 phosphate, 1 sodium, and 1 hydroxide. When I go to this side of my equation, I can start doing the same. But here I'm looking at water. I can see sodium and and that's not phosphate. I wrote phosphorus. Let me fix that. That looks better. So here I've got sodium and phosphate, which will work down here. But over here, water, I don't have hydrogen and hydroxide. But here's your trick, and this is what can be helpful. If you notice there's a hydroxide in there, you can rewrite water. Water can be H2O, or you can write HOH. So now you can see where the hydrogen is and hydroxide. Here's a hydroxide, and then you've got your hydrogen. And that can make balancing these ones a little bit easier. This is a good strategy with water. Expand it, because it's often written in its condensed form. So if I take a tally now, hydrogen, there's 1. Phosphate, there's 1. I've got 3 sodiums, and I've got 1 hydroxide. So here, if I want to start balancing, I'd probably pick the sodium. So it's not hydrogen or oxygen, and I want to make 3 of them. So if I put a 3 here, 3 sodiums, now it also means I have 3 hydroxides. Then I take a step back. My sodiums are balanced, my hydroxides are not, and my hydrogens still are not. So I'm going to go to my hydroxide. I want to make 3 over here, so I'm going to put a 3 in there. That'll make 3 hydroxides, but it'll also make 3 hydrogens. And now when I take a look, I've got 3 and 3, 1 and 1, 3 and 3 on both sides. So now everything is balanced. So hopefully going through these 4 examples and reviewing lots of rules with writing different types of equations and balancing will help get you started on being able to balance challenging questions and also test your knowledge of your nomenclature. Get as much practice as you can with balancing, because again, it's a tool that you're going to see in every other chemistry course you probably take in the next few years.